Okay, so then the first such generative model that we'll actually talk about in a little bit more concrete specificity are autoregressive models. So autoregressive models, we're actually going to take a slight detour and talk about a really general idea behind all of generative modeling, and that's the idea of maximum likelihood estimation. And maximum likelihood estimation is actually a quite general procedure that we can use to fit probabilistic models given a finite set of samples. So the idea is we're going to write down some explicit function for the density. We said that some methods are going to explicitly model the density. Well, let's do it with a neural network. Let's write a neural network that's going to input the data X, input the weights W of the neural network, and it's going to spit out a number that's going to tell us what is the density. So then, we're going to train the data, we're going to, given a data set of samples, x1, x2, xn, we're going to train the model via this objective function. We want to find the weights that that make the data set most likely, right? Where we want to set, because as we vary the weights, it's going to vary the kind of densities that are being modeled by the network. So we want the network to select the density that maximizes the likelihood of the data. Note that we said likelihood rather than probability. That's a deep philosophical rabbit hole you can fall into. The difference is what we're varying, right? If you think about probability, you kind of imagine that the density is fixed and we're sort of sliding X around and changing what is the probability of X under a fixed distribution. When you talk about likelihood, instead you're often fixing the samples X and you're varying the distribution itself, and saying, how does the probability density of those samples change as we vary different distributions? So you have to think about very carefully in these equations what's being fixed and what's varying. So in this process of maximum likelihood estimation, what we're doing is varying the distribution that the neural network is modeling to try to maximize the probability of the fixed set of samples we have from that distribution in our training set. Right? And I guess the unsaid thing behind all of this is that we assume that there is some underlying true probability distribution, P data, which was used by the universe to generate the data that we are seeing. And in some sense, always what we want to do is try to model that true underlying unknown distribution P data. And we can never access P data because we don't have this omniscient view of exactly how the universe works. But instead, we get some samples from P data that the universe has given to us. And what we're trying to do through our learning procedure is uncover that unknown distribution P data, given a finite number of samples from that unknown distribution. Right? So one procedure that you can go about this is let's select the distribution that makes the data that I saw actually most likely. And that's the objective, that's the maximum likelihood objective function. Right? And then a standard trick that we do here, right? We assume that the data was IID, independent and identically distributed. So we assume that each one of those X's was drawn from that true P data distribution. And now we want to maximize the joint distribution of all the data that we saw. But because it's independent, we can factor it down, into independent likelihood of each of the independent samples. And then the common trick that we always use is the log trick. So we know that log is a monotonic function. So if you maximize something, it's equivalent to maximizing the log of that something because log is a monotonic function. And then log is also very convenient because it swaps sums and products. So it's common to just, instead of maximizing the likelihood of the data, instead we're going to maximize the log likelihood of the data, and that's the same as maximizing the likelihood. And once we apply the log, then that product splits into a sum, and sums are easier to handle. And now, we slot in our neural network, because our neural network is now maybe directly outputting the density. So this gives a direct objective function that we could use to train a neural network. This gives it a very concrete loss function that we can use to train a neural network to solve this kind of generative modeling problem. But we need a little bit more structure here to actually make progress. This idea of maximum likelihood estimation is very general. It doesn't really assume anything about the kind of data. It doesn't really assume any structure in the data. And we, in general, need to put a little bit more structure on this to make some progress. So autoregressive models basically make the assumption that there is some canonical way that we can take our data X and split each data sample X into some sequence of subparts, X1, X2, XT. You got to be careful with indices here. Here I said the subparts, these are subparts of a single sample. So I use a subscript. And the previous slide, we had superscript to indicate different samples, X1 to Xn. So be careful with that. Superscript on this slide is different samples X. Subscript on this slide means different parts of the same sample. So we assume that there's some canonical way to break up our data sample X into some sequence of subparts. And now we can apply the chain rule of probability. So probability of X is just the joint probability of all of the subparts, X1 to XT. And then given any probability distribution, you can always break it apart into this chain rule. That probability, the joint distribution of all these variables is equal to probability of the first one, times probability of the first given conditioned on the first, probability of the second conditioned on the first, times probability of the third conditioned on the first and the second, et cetera, et cetera, et cetera. Right? And this is the chain rule of probability. This requires no assumptions. This is always true of any kind of joint distribution of random variables. And then this sort of gives us our objective function. Or then you could basically train a neural network that's going to input, the previous part of the sequence and then try to give us a probability distribution over the next part of the sequence. Does that sound familiar? Does that sound like something we've done before? RNNs, yes. So that's exactly what an RNN is doing, right? An RNN has this very natural structure that, by passing hidden states along forward through time, the hidden state always depends on the beginning of the sequence up to the current point. So then there's a very natural way to use RNNs for autoregressive modeling. So you have your sequence of hidden states that are basically summarizing your sequence. And then from each hidden state, you predict probability of the next piece of the sequence, conditioned on all earlier parts of the sequence. And that basically is an RNN language model that we saw some lectures ago. Have we seen anything else that can do this? Yes, transformers, and particularly masked transformers. Right? So we talked in a transformers lecture, transformers can also be used to have this structure, where by masking out the attention matrix in the right way, we can make each output of the transformer depend on only the prefix of the sequence. So we can also use transformers for autoregressive modeling. And they're very commonly used for this. Okay. So this is, but the problem with autoregressive modeling is that you need to break your data up into a sequence. And this is very, very natural with text data, right? Because text data is naturally a 1D sequence. And it's even a 1D sequence of discrete things, which is great because it's very easy to model probabilities of discrete things. We've been doing that all semester, with our favorite cross-entropy softmax loss, right? The cross-entropy softmax loss is always, distribution over discrete, fixed discrete number of categories. The network predicts a score for each one of those, normalize it with a softmax, train with a cross-entropy loss. We know how to do that. So that's why these things fit very naturally for language models, because language is already discrete. Language is already a 1D sequence. So there's a little bit of fuzziness in how, there's a tokenizer in there. We're not going to get into that. But these are very naturally well suited to language problems because language is already 1D. It's already discrete. Images are more tricky because images are not naturally 1D. Images are also not naturally discrete. We often think of images as continuous, real valued things. So these don't naturally fit quite as nicely onto images. But, you got a hammer, you're going to whack some nails. So, people definitely apply autoregressive models to images in kind of a naive way, at least some years ago. So, one thing you can do to, model images with autoregressive models is to treat an image as a sequence of pixels, right? And in particular, each pixel is actually just 3 numbers, and, in most displays and in most representations of images, those numbers are actually discrete. Right? So most JPEGs or PNGs, most of the file formats we use to store images, are typically 8-bit per channel. So there's actually, only a fixed number of values that each pixel can take. So a pixel is just three single byte values. A single byte is just like an integer from 0 to 255. So a pixel is just 3 integers, each integer can be 0 to 255. So what we can do is, take our image and then rasterize it out into a long sequence where each element of the sequence is one of the subpixels values of our image. And now we've turned our image into a one-dimensional sequence where each entry in that sequence is a discrete value. So you can apply autoregressive modeling directly to that sequence, in exactly the way that you might have for a language model, using an RNN or a transformer. Can anyone spot a problem with this approach? Too long, very expensive, very, very expensive. So, a kind of reasonable image that you might want to model is maybe 1024 by 1024. That's not even that high resolution, really, but that's a pretty good resolution. But if you have 1024 by 1024 image, that's going to be a sequence of 3 million subpixels. People actually can model these days sequences in the millions, but it gets very, very expensive. There's got to be a more efficient way to do this. So there were some papers a couple years ago where people applied these sort of autoregressive models directly to pixels of images, but they were not super successful, I think, because they're very difficult to scale to high resolution. So a spoiler alert that we'll talk a little bit more next lecture is that this actually has made a resurgence in the last couple of years. But the trick is to not model the individual pixels in the sequence as individual pixel values, but instead to use some other kind of process or procedure or model, neural network maybe, to break that image into a sequence of one-dimensional tokens. So that's something we'll talk about a bit more next lecture. But this at least gives you the sense of what is an autoregressive model, what's the probabilistic formulation of them, how do you apply them to language, how do you apply them to images. So then from autoregressive models, we next turn to variational autoencoders. And variational autoencoders are pretty fun. So we talked about, in these autoregressive models, we talked about, we're trying to do maximum likelihood. We broke up our data into a sequence of parts. We're trying to maximize the likelihood of the data. And variational autoencoders are going to do something a little bit different. Instead, there's still going to be an explicit method. There's still going to be some kind of density that we can compute, but it's going to be intractable. We're going to be able to approximate it. Why are we going to do that? We had a perfectly good method that computed densities exactly, and what we're going to give up for that is we're going to gain something. We're going to gain the ability to compute reasonable latent vectors over our data. We're going to have, vectors that represent our data that pop out naturally from the learning process. And those vectors are going to be useful in their own right. And the ability to get access to those latent vectors is going to be useful enough to us that we're willing to give up computing exact densities and instead settle for these approximate densities that are actually lower bounds on the true density. Oh, the motivation for breaking stuff up in a sequence in autoregressive models, because it factors the problem. It makes each part easier to model, right? So imagine you're doing language modeling, right? And you have a vocabulary of V words. And I want to model the probability of 2 words jointly, right? How many possible 2-word sequences are there? There's V squared. How many possible 3-word sequences are there? There's V cubed. And in general, if you have how many T-word sequences with a vocabulary of V are there? It's, V to the T, right? So that's bad. It grows exponentially. If you wanted to directly model the joint distribution of a sequence of T things, the number of entries in that discrete probability distribution you need to model is going to grow exponentially with the sequence length. And that's quickly going to become completely intractable if we want to go to long sequences. So then the reason we break that up is so that we don't have to model it all at once. We factor it in this way and predict only one part condition on the previous parts. Good question. Can we apply the log trick to mitigate that? Yeah, exactly. So in practice, you'll never actually see these probability density values modeled. Almost always you're going to work in log probabilities instead. So the model that outputs, the model is going to output log probabilities. You're going to compute your loss in log space. For numeric stability, you're almost going to compute everything in log space in practice. So then the P of X is being generated because at the output, at the top of the transformer, it's outputting a probability distribution over the next token conditioned on all the previous tokens. And it does that for every point in the sequence. So you could actually recover this exact probability density value by multiplying out the values at all points in the sequence. So if I have an input sequence, I pass it through the transformer will have predicted at every point in the sequence what is the distribution over all the tokens conditioned on the earlier part of the sequence. And I can compute what was the actual next token, what was the predicted probability of the next token, and then multiply all of those across the entire sequence. So that's how we can recover the exact density value out of one of these autoregressive models. And that actually would apply either to an RNN or a transformer. Okay. Good questions. So then in a variational autoencoder, things get hairy. So we're actually going to drop the V and talk about autoencoders for just a couple slides, because I don't think we've done that yet this course. So in a non-variational autoencoder, this is basically going to be an unsupervised method for learning to extract features Z from inputs X without labels. And this actually, is kind of in this vein of self-supervised learning that we just talked about. And our notion is that the features ought to extract useful information about the data, right? Maybe they somehow implicitly encode what is the identity of objects in the image, how many of them there are, what are the colors of them. We want this feature vector Z to contain useful information about the input X. And this encoder itself could be a neural network of any architecture. It could be an MLP, transformer, CNN, whatever you want. But it inputs our data X, and then it's going to output some vector Z. And then the question is, how do we learn this without labels? We actually saw a lot of examples of this in the previous lecture, but there's a very simple one, which is just try to reconstruct the input. So we're going to now have a second part of the model called the decoder, which is going to input the Z and then output back an X. And we want, and I dropped the X. And we're going to train this thing so that the output from the model should actually match the input. This is in some sense the stupidest loss function ever. We're just training the model to mimic the identity function. Why do we do that? We already know the identity function. Why are we expending a lot of flops and training a neural network on a big data set to just learn the identity function that we already know? It's because we're going to bottleneck it in some way. If this model had infinite capacity, for example, if that z vector was very wide, if there were no constraints on the learning, I would expect a neural network to just nail this problem. But we don't want to do that because we explicitly don't care about learning this objective. We already know the identity function. We don't need an expensive neural network to compute it. What we want to do is force the network to try to learn the identity function under some constraint. And the constraint that you often use in a traditional autoencoder is by bottlenecking that representation z. In particular, that means that vector z in the middle is going to be much, much smaller than the input x. So your input x might be a high resolution image, maybe like a 1024 by 1024 image that we said is composed of 3 million floats. But then that z might be like 128 dimensional latent code. So the model is now asked to solve this problem where I want to reconstruct the output, reconstruct the data x, but squash it through this like bottlenecking representation in the middle. And we hope that this is going to force the model to learn some non-trivial structure about the data by squashing it through this representation in the middle of the network. And then after we do this, we can apply our normal self-supervised learning trick, where, you could throw away the decoder, and then use this Z to initialize some supervised model for some downstream task. The same story as in the self-supervised story that we just saw. But what if we actually want to use this to generate data? Then what we'd really like to do is somehow the opposite of the self-supervised story. What we'd really like to do is throw away the encoder and instead be able to somehow sample Z's that match the kinds of Z's that the model learned to represent data as. And if we had some procedure for sampling Z's that matched the data distribution in some way, then we could sample a Z, pass it through our learned decoder, and now generate a new sample, right? And now this is an implicit method, right? You said that there's no densities floating around anywhere, but if we had a way to do this, it would be a way to draw samples from the model without explicitly modeling the density in any way. But the problem is that, we've just kind of kicked the can down the road here a little bit because we said if we want to generate images, we want to generate X's, we have a data set of X's. How do we do that? We said we're going to solve that by training this autoencoder, and now we have a data set of Z's and we need to sample in Z space. It's not any easier. So we're kind of stuck. And the idea of variational autoencoders is, what if we could force some structure on the Z's? If you have this traditional autoencoder structure, you're not forcing the model to impose any known structure on the Z's. You're just asking it to reconstruct the data, given its latent representation. But what if we had some mechanism to force the Z's to come from a Gaussian distribution or some other known distribution? If that were the case, then we could just draw a sample at inference time after this model is trained, draw a sample from that known distribution, pass it through the decoder, and now we would have our sample. So forcing these autoencoders to be probabilistic and to enforce a probabilistic structure on that latent space exactly is what a variational autoencoder tries to do. Why variational? It's a long story. It has a long history a lot of history around that terminology in the literature. But basically variational autoencoders are a probabilistic spin on our traditional autoencoder. So it's going to learn latent features Z from raw data, and then we'll be able to enforce a structure on that learned latent space Z such that we can sample from it at inference time after the model is trained and generate new samples. So more concretely, we'll assume that our training data, xi, again, note here the superscript I means these are different independent samples of x. We assume that each xi was generated from some underlying latent vector z. That there's some zi that's lurking under the surface associated with every xi. And in the universe's procedure for generating data, first it generated the zi, then it generated the xi from the zi. And everything that the universe needed to know in order to generate the image that we saw was contained in that latent vector z. But we can't see those latent vectors z. We can never observe them. We don't have a data set of them. Right? So the intuition is that X is an image, Z is some kind of latent feature representation that tells you everything you would ever need to know about that image, but you can never observe that latent vector. And then after training, we could generate a sample by, and the other constraint is that we're going to force those Z's to come from a known distribution. So then after the model is trained, then we can do exactly what we just said, draw a Z from that known distribution, pass through the decoder, that's going to give us a sample. And then we'll typically assume a simple prior. Almost always a unit Gaussian distribution is by far the most common. So then how do we possibly train this? Like, this feels like an impossible problem. We want to basically train this network that's going to, get these z's, find a z for every x. We can never observe the z's. This seems impossible. What are we going to do? We're going to go back to a maximum likelihood, right? If we indeed had a data set of x's and z's, then we could use maximum likelihood to directly use the same kind of log trick, maximize the log probability. We could use the exact same thing that we previously saw. And then train a conditional generative model, p of x conditioned on z. But we don't know z. But let's pretend we do for a moment. Because we don't know z, we could try to marginalize, right? We know that p of x is equal to, maybe there's some joint distribution of x and z, that must exist, even though we can't observe it. And then in principle, you could integrate out the z to marginalize over it to get a p of x. And then maybe we could do, pretend there's a joint distribution x and z, marginalize out the z somehow, and still do maximum likelihood. Maybe, let's see how this works. So this term and then here we've also used the chain rule to break up that p of x given z, and that joint probability p of x and z into p of x given z and just p of z. So this p of x given z, that's okay. We could compute that with our decoder here on the left. That's a neural network that we're hoping to train. This p of z term is okay. We're going to assume that that's a unit Gaussian or some other simple distribution that we can compute or reason about. But this integral kills us, right? In general, we have no feasible way to integrate over the full space of a neural network's input, right? This p of x given z is going to be some very complicated function that's modeled by a neural network. There's going to be no way that we can analytically or exactly integrate this. You can train neural networks for individual parts here, right? So the whole underlying notion here, whenever you're doing this probabilistic modeling, is we're going to write down some probabilistic terms. Hopefully some of them are going to be simple distributions that we can write down analytically and reason about. Some of them are going to be learned neural network components. So we're kind of assuming that probability of x given z is going to be some neural network that we could in principle learn via maximum likelihood. But we're starting to write down what objective could we use to learn that neural network via maximum likelihood. And we're out of luck here because you have no way to integrate over z. You could try to approximate that integral via some finite sampling, but in general that's probably not going to work very well because this z is a super high dimensional space, and trying to doing an approximate numerical integral in the inner loop of your training is not going to be a very good idea. So we could try something else. Bayes rule. That's the other thing we always do in probability. So let's try Bayes rule. If we have Bayes rule, we have another formula that we can use to write down p of x. Right? So p of x we can write down in Bayes rule, using Bayes rule in this equation on the screen. Let's see what we can do with these terms. So this one, okay, p of x given z, again, we can compute that with our decoder. P of z, again, okay, this one's, we assume this is Gaussian, so we can compute something with it. There's no integrals here, that's good. So we're in good shape. But now we're out of luck. This p of z given x term, this posterior of z given x, we have no good way to compute this. In order to compute this term, you would also need some kind of integral. Out of luck. We can't compute it. What are we going to do? Okay. Let's use another neural network. So the variational autoencoder trick is there's that probabilistic term on the bottom here, a Bayes rule that we can't compute. Let's just slot in another neural network to try to compute it for us. So we're going to have another neural network Q with different weights, phi, that's going to learn a different conditional distribution, probability of z given x. And the whole thing is we want this other neural network to try to approximate the true p of x given z of the first neural network. And you can't really enforce this in general, but let's put a neural network there and see what we can do. So then if we could somehow have this other neural network that was approximating this term on the bottom that we can't compute, then we could go and compute our likelihood and do maximum likelihood, and we would all be set. So that's kind of what we do when training a variational autoencoder. We're basically going to jointly learn two different neural networks. One is the decoder, which inputs the latent code z and outputs a distribution over the data x. The other is an encoder, which is going to input the data x and output a distribution over the latent codes z. And each of these are going to be separate neural networks that are separately trained with their own independent weights. There's a question you might have, which is, how can you possibly output a probability distribution from a neural network? That seems confusing and hard and unclear. So the trick here is we're going to actually force everything to be a normal distribution, and we're going to have the neural network output the parameters of the normal distribution. So typically for the decoder network, we're going to assume that the output distribution from the decoder is going to be diagonal Gaussian, where the entries in the diagonal are the pixels of the neural network. And the model is going to output the mean of that diagonal Gaussian distribution. And typically for the decoder, we'd assume a fixed variance or standard deviation sigma squared. Now for the encoder network, same idea. The model is going to input a data sample X, and then it's going to output the parameters of a Gaussian distribution that model the distribution Q of Z given X. So in this case, the encoder network will output one vector, which is the mean of that Gaussian distribution, and another vector, which is the diagonal of the covariance of that Gaussian distribution. And here it's very important that we assume the diagonal structure, because otherwise we would have to model, H squared kind of entries in that full covariance matrix. Right? So here, right, you imagine an image that's H by W pixels. So that means that the entries in your diagonal matrix are like the full, you could in principle model the full covariance across every pair of pixels in the image, but that would require H squared, W squared entries, and that would be too big. So instead, we'll just ignore any kind of correlation structure among the different values. And now that means that the diagonal covariance is now a vector that's the same size as the data itself. Right? So that means this mu of Z given X and this sigma of Z given X are both vectors of the same shape as Z. So we basically treat the have the neural network output two vectors of the same shape and then treat them as the parameters of this Gaussian distribution. So that's how we can output a distribution from a neural network. If you do maximum likelihood on this thing with a fixed standard deviation, it actually becomes equivalent to L2. And that's a nice trick. And the reason you want to do that is because trying to model the diagonal, you could in principle try to model the same thing on the decoder and try to model the individual, a separate variance of every pixel, but that would be kind of useless. Because that would be, if you're not modeling any covariance structure among the pixels, that would basically be saying that each pixel is allowed to, vary a little bit, and the amount that each pixel is allowed to vary kind of depends on the pixel. And then sampling from that distribution would basically amount to, fixing the mean and then adding per pixel independent noise that's scaled by the per pixel variances. And that would not be a sensible thing to do. So in general, for the decoder, you kind of cheat a little bit. And you kind of pretend it's outputting a probability distribution, but in general, we're never going to sample from that distribution. Instead, we're always going to output the mean. Does that make sense? Yeah. And then it turns out, if you write this down, that constant sigma squared just comes off as a constant in the front. And in practice, maximizing the log likelihood of a Gaussian distribution with a fixed variance along the diagonal, is equivalent to minimizing L2 distance between the mean and the X, which is kind of nice. Yeah, good question. Is there some kind of weird invariance or non-invariant structure here with the pixel shifting? That would be more a property of the architecture that you would choose to build the neural network. So you could try to build into your network architecture that's predicting these. You could try to build some invariance or equivariance properties into the architecture. But yeah, you're right that in general that's not accounted for at the loss level here. Okay, so now we've got this idea. We've got an encoder, a decoder. One is inputting X, outputting a distribution over Z. Other is inputting Z, inputting a distribution over X. What's our training objective? And here's the one slide where we're going to do some math. But we'll see. So here basically the idea is we want to do maximum likelihood. That's usually the single thing that we want. That's the guiding principle behind a lot of objectives in generative modeling. So we want to maximize log P of X. And then we can use Bayes' rule to write that as log P of this Bayes' rule expression. Right? This is an exact equivalence. Now we're going to do something silly. We're going to multiply the top and bottom of this by our Q of Z given X. Remember, we just introduced another neural network Q out of nowhere that was modeling this other distribution Q of Z given X. And now we're going to multiply that density term on the top and bottom of this Bayes' rule expression. Now we're going to do some logarithm math. And if you're, have some foresight, you'll for some reason decide to rearrange these terms in this particular order. And I've color coded them so you can later go and track which term went where. But we do some logarithms and break this up into three separate terms. Now you need to make another magical observation, which is that this P of X, actually does not depend on Z, right? So far, this sequence of three terms, this is all an exact equivalence. These are all exact equalities. So even though there's a Z in this expression, it actually doesn't depend on Z because all the Z's would cancel out. And if you have something that doesn't depend on Z, you can always wrap an expectation, over Z of that thing. So in this case, we know that this is a P of X. We can always feel free to wrap an expectation of Z sampled according to any distribution that we want, of P of X. And because that internal thing does not depend on Z, this is always true for any distribution that we might choose to take this expectation over. Okay. So then, because expectation is a linear thing, we can apply that expectation to each of these three terms upstairs. And now we have these three terms, each of which looks very mysterious. But if you had a lot of intuition about probability, you memorized all these formulas that you may have seen in an earlier statistics or probability course, maybe you could learn to recognize some of these. So this first one, we're going to carry down as it was before. And these second two are actually KL divergence, terms. So the KL divergence is a kind of measure of dissimilarity between probability distributions. And it just so happens to have this exact definition of these latter two terms. So we can rewrite this exactly as this first term, which is this expectation, blah, blah, blah. We'll talk about it. And then plus these two other KL terms. So these two KL terms are basically measuring dissimilarity, or measuring discrepancy or dissimilarity between these different kinds of probability distributions that we have floating around on this slide. And now these all look kind of crazy. But if we stare at each of these terms, we can actually recover a interpretable structure, an interpretable meaning for each of these three terms. This first one is actually a data reconstruction term. If we walk through what this is saying that we're going to sample a Z, and the way we're going to sample the Z is by Q of Z given X, which is our encoder. So we're going to take our X, pass it to the encoder. The encoder is going to predict a distribution, Q of Z given X. Then from that predicted distribution, we're going to sample a Z. Then we're going to take an expectation over all such Z and maximize the log probability of X given Z. So this is basically a data reconstruction term. It's saying that if we take an X, a data point X, run it through the encoder to get a distribution over Z, and then pass any sample of that predicted distribution over Z into the decoder, we're going to recover X. So this is a kind of data reconstruction term. The middle one is a prior term. This is saying we want to, this is measuring the KL divergence between Q of Z given X and P of Z. So remember, Q of Z given X, this is the encoder is inputting the data X and outputting a distribution over the latent space Z. So this is the predicted distribution over the latent space of the encoder. And this other term, P of Z, this is the prior. This is the prior that we assumed for the latent space, usually diagonal Gaussian. So this term is basically saying, the model is predicting distributions of Z given X, and we want those predicted distributions to match the simple Gaussian prior that we had previously chosen. So this is just measuring how much does that latent space that's learned by our model match the prior. And this third term gets us in trouble. So this third term is Q of Z given X. So that's the predicted distribution over Z given the input data X to the encoder. And how much does that match P of Z given X? So that's this flipped around distribution of what the decoder is modeling. And this one, we're out of luck. We cannot compute this term. Because remember, what got us into trouble in the first place was this P of Z given X. The whole reason we introduced Q was because we could not compute this P of Z given X. So now, what do? We're gonna throw it away. Because we know that KL divergences are always greater than or equal to 0. So we know that this last term, because it's a KL divergence of two distributions, even though we cannot compute those distributions in general, we know that it must be greater than 0 because that's a well-known property of KL divergences. So we can throw it away and get a lower bound to the true probability. So if we throw away that last term, then we know that log P of X is greater than or equal to those two terms, our reconstruction term and our prior term. So this will be the loss that we use to train our variational autoencoder. And the idea is that this is an approximation to the true log likelihood. This is a lower bound to the log likelihood. So if we maximize the lower bound, hopefully that will also maximize the true log likelihood, even though we're not doing it exactly. So that's our training objective for variational autoencoders. So that's kind of the summary. You're going to jointly train an encoder Q and a decoder P to maximize this variational what's called a variational lower bound on the true data log likelihood. And this is also sometimes called the evidence lower bound or elbow. So it's just the elbow, where we're going to maximize the elbow. And it has this particular term. We have these encoder network, this decoder network. That's what we do. So then, to kind of walk through what the training procedure looks like more explicitly, we're going to have this neural network encoder, inputs the X, outputs the distribution over Z. Then we're going to apply this KL term to the predicted distribution. And in particular, because this is going to force the predicted distribution to be unit Gaussian. So it's basically going to encourage the predicted mean to be 0 and the predicted sigma to be diagonal ones, to be all ones. Then once we get to those predicted distribution from the encoder, we're going to sample from that predicted distribution using this so-called reparameterization trick that allows you to backprop through this. So then we draw a sample z from the predicted distribution. Once you get the predicted this sample z, you run it through your decoder to get your normal distribution predicted by the decoder. And then you apply your reconstruction term of the loss to the output of the decoder. So even though this looked like a large, scary slides of math, it actually led to like not too crazy of a training objective for this thing. And I think this variational autoencoder is actually very interesting because these two losses fight against each other in a very interesting way. So because we're basically forcing the model to bottleneck through this latent space z, and these two terms kind of want different things from the latent space. So the reconstruction loss kind of wants the sigma to be 0 and the mu x to be a different and unique vector for each data x. Because if that were the case, then we could perfectly satisfy the reconstruction objective. We would have a separate unique vector for every data point, and there would be no probability in there. We could perfectly reconstruct everything. So that's kind of what the reconstruction loss wants. But the prior loss actually wants the sigmas to be all 1 because it wants it to be unit Gaussian, and it wants all the mu's to be 0. Which is very different from what the two losses want. So in the process of training a VAE, you're asking these two losses to fight against each other to try to find some equilibrium between reconstructing your data well and forcing your latent space to be close to your prior. And then once you've trained it, then you can sample Z from your prior, run through the decoder, and get a sample. Another nice thing is that because your latent space was diagonal Gaussian, there's also a notion of statistical independence across the different entries in your latent space Z. So you can vary them separately, and maybe those separate dimensions often encode something useful or interpretable or orthogonal about your data. So in this case, we took a VAE, trained it on a data set of handwritten digits, and you kind of see that as we vary two dimensions of the latent space, the digits kind of smoothly morph from one kind of category into another. And this is a pretty common property of VAEs. So that's basically it for today. To kind of recap what we talked about supervised versus unsupervised learning. We talked about these 3 different flavors of generative modeling. And then we talked about one branch of this family tree of generative models. So then next time we're gonna come back and talk about the other half of the family tree of generative models, in particular talking about generative adversarial networks and diffusion models.